Okay, so I left you with an example of a double-line spectroscopic binary problem where I gave you the rate of velocity amplitudes of the two stars and the period. So you can see here we don't need to know the distance to the system at all, which is good, because often these systems can be quite a long way away, not too far away even for parallax patch. But as long as you can measure the rate of velocity, as long as they're bright enough to take spectrum, you can get this information. Okay, so let's do the sum of the masses part first. Okay, so you need to substitute everything in again, make sure everything's back in SI units. So the period is 8 hours. So convert to seconds from there. And then you've got the rate of velocities. Don't forget that I gave you those in kilometers per second, which is sort of typical unit that's measured for rate of velocities in astronomy. And so that needs to be converted to meters per second, as in here. Put everything in, as I said, assume inclination angle is 90 degrees, so that term just goes to 1. And we get 4.3 solar masses as the mass of those, the sum of the masses. Of course, if we didn't know what I was, this would be a lower limit, not the actual value. But let's assume it is here. So then, to solve for the individual ones, we just go to the mass ratio, which is given by the ratio of the rate of velocities. Okay, so you can just work through that to then give you the individual masses. So here we've got 3 solar mass star and a 1.3 solar mass star. So again, the rate of velocity amplitude for star 1 is lower than it is for star 2 because it's the more heavier star and it's nearer the center of mass. So it has a lower velocity. So you can always sanity check your answers by thinking about that. Okay. So that's how that sort of works in practice to derive masses of stars using sort of typical values. Okay, so that was a double-lined spectroscopic binary. But there's another type of spectroscopic binary, which where we basically only see one star in the spectrum moving to and fro. Okay, so we just see the one set of spectral lines. So the other object is basically too faint or too weird, as we might see in a moment, to have spectral lines. Okay, and so you just see this. You just see one set of spectral lines going to and fro. This was the double line system, as we had before, where you've got 2 stars doing up, ding, 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 ding. Here we just got one set of lines doing this, okay, and that's all you. So you can tell there's a binary there, and you've got the information for one of the stars, but you don't have the information for the other stars because you can't see its lines in the spectrum. So you might think we're on a bit of a hiding to nothing here, but as I'll show you, then this does lead to some amazing discoveries. So let's assume that we can only see star 1. So we know what VR1 is from the same kind of data as before. So we've got a rate of velocity curve, but only one star on it. And we don't know what VR2 is. Okay. So let's carry on. Again, this will look a bit complicated, but again, try and bear with it. So we need to eliminate VR2, eliminate the unknowns in terms of things that we know. So we know VR1, so we can relate VR2 to VR1 again using the mass ratio, center of mass idea, and put it in the same formula that we just had for the double line system. So we can start to try and simplify this complicated looking formula down a bit. So we've got a common factor of VR1, we can take that outside, and we can re-express the function in mass on the top. So VR1 cubed is popped up over here. Okay, we've also now got a common factor of m1 plus m2 on each side, so we can do one more bit of tidying up and bring all the unknowns on one side and all the knowns on the other. So we will know the period and we will know VR1, and that's it. So this is all we're going to have for a single line spectroscopic binary system. So you can see that, it's how are we going to solve this for the individual masses? Well, it's impossible, really. So the only way to make progress is we could make some kind of estimate of M1. This is often the way it works. So star 1 is the one we can see. So we will have the spectrum of star 1. So even though I said previously that, if you know just from the spectrum, you can't always get a very accurate mass, but you can get an estimate of a mass. I mean, if you can spectral type it and it's a main sequence star, for instance, then you can have a reasonable estimate of the mass. It won't be accurate to a few percent like you get from the full visual binary system, but it might be accurate to 20, 30%, something like that. And you could always, put a sort of a lower limit on it. So if you think you've got an estimate of M1 and you've got some idea of what the inclination is, again, often we've no idea what it is, but in certain circumstances we do know what it is, then you can solve for M2, which is, so M2 here is basically an unseen companion. So can we estimate the mass M2 of an unseen companion to a sort of known star? So why is this formula so important in astrophysics? Well, let's sort of think for a moment about, the ultimate unseen companion. So I would say the ultimate unseen companion is one of these. Okay, this is obviously an artist's impression because we can't see it. Well, until recently. So this is an artist's impression of a black hole. Okay, so we met the black holes before. We have this idea of an event horizon inside which light cannot escape because gravity is so strong. So that's what's supposed to be indicated here with this black thing in the middle. And you've got around it, which is giving us the clue to what's going on here, is a sort of disk of material that's swirling down into the black hole. And you've got artist's impression of sort of light bending effects because the gravity is so strong that light is getting bent around all over the place here as well. But let's not worry about all of that. Where's this material coming from? Well, what happens if you have a black hole next to another star in a binary system? Okay, so ignore the catalog number here. This is just a schematic diagram of a particular system. So if you've got a black hole orbiting another star, now a black hole is, has an incredibly strong gravitational field. Okay. So it will have the potential to pull material off the surface of the companion star and pull it onto itself, okay, as it goes round. And because everything's orbiting around each other, you've got angular momentum here, everything ends up spiraling around in a disk and then slowly sort of disappearing down the plug hole here, if you like, down into the black hole. So the black hole will accrete matter from its companion star. As it does so, it gives up a huge amount of gravitational potential energy, so that gets turned into heat. And so the gas circulating near the black hole here is extremely hot, millions of degrees. And the red squiggles here are meant to represent X-rays coming out of here. So you've got very hot gas, just like in the solar corona, but very dense hot gas this time. So you will have a strong source of X-rays. And so that's how these systems are found. Okay. So when X-ray satellites started surveying the sky, they found these bright sources. Often they were sort of variable X-ray sources because this thing's going around in a binary. When they looked with optical telescopes, they just found a normal looking star, but then they found that it was a single line spectroscopic binary because it was orbiting around the black hole. Okay. But you can't see any of this directly on an image. This would be far too close. All you know is that there's X-rays coming out of here, so that points to some energetic accretion onto a compact object. And you've got it's in a binary system, but you only know the parameters of this object. So you can estimate the mass of this object from its spectrum, and you can measure the radial velocity parameters and apply that formula we just mentioned. Okay. And basically all of that construes to give us a lower mass, again, to this compact object here. Now, when we discussed stellar evolution, I mean, we saw that there's, 3 different types of compact object at the end of a star's life. Could be a white dwarf, could be a neutron star, or it could be a black hole. So how do you prove that this companion would be a black hole? Well, again, I'm not going to go into the details here, but basically for objects like white dwarfs and neutron stars, they're held up by these quantum mechanical effects on electrons or neutrons. But fundamental physics tells you that there is an upper mass limit to those types of objects. So there is an upper mass limit to a neutron star of about 3 solar masses. We saw that on one of the diagrams at the end of the HR diagram lecture. So if you can find a compact accreting companion to a star that is more massive than, and prove that it's more massive than 3 solar masses, then it basically has to be a black hole. Okay? Can't be anything else. So that is what has been done several times now. There's a good handful of each of these type of objects. So this is the type of data. So again, this is one of these radial velocity curves that I just showed you, but this time for a single line spectroscopic binary. So you can see radial velocity here in kilometers per second. Again, it's whizzing around in about 8 hours. Huge amplitude of 500 kilometers per second, something like that. So again, higher speeds means more massive objects. Okay, and this is a so-called X-ray binary. It's got X-rays coming out of it. And basically this radial velocity curve and applying that formula proves that the invisible compact companion is 5 solar masses, which is far too big to be a neutron star. So it's this kind of data that tells us that the object is indeed a black hole. Okay. So when the next time you're down the pub or cafe or something and you tell someone you're studying astronomy and they immediately start asking you about black holes, because they always do, and they ask if you believe they exist, or how do you know they exist, then you take them through the derivation of Newton's form of Kepler's third law. You take them through the derivation of the single line spectroscopic binaries, and you show them one of these curves and you say, there you go, that's why black holes exist. Okay, so let's summarize the whole lecture. So visual binaries are the only things that really provide these accurate masses, to a few %. But as I mentioned, they need to be nearby, and so there aren't that many of them known. There are many, many more spectroscopic binaries known, okay? Because all you need is the spectrum. You don't have to resolve the 2 stars then, or you can't resolve the 2 stars. Often you don't get the accurate masses because you can only just constrain the masses because we don't know the inclination. Now, there is an exception, which I'm just mentioning here. There is certain circumstances when you really do know the inclination. Okay, I'll just go back to that schematic here. And that's if 2 stars are, if their orbital plane again is perpendicular to the sky, then one star will go in front of the other star and eclipse it. Okay, so when this big star goes in, or if it orbits in front of this other object, it will block out the X-rays from that object, and so that you know that you've got what's called an eclipsing system. So there's a whole load of objects out there called eclipsing binary stars. Doesn't have to be a weird object like a black hole. You can just have 2 normal stars that are eclipsing. If you want to, you can read about them in the textbook, but they're not. I'm not going to ever ask questions about them. They're not core to this module. They only come in here as a way of, if you know your system is eclipsing because the brightness level changes, so you see little dips in the light curve, then you know your system is eclipsing. And then you know that I must be close to 90 degrees. And there are quite a few black hole systems like that, where you actually do know the inclination because it's eclipsing. So in that case, you then have really good measurements. Okay. So the spectroscopic binaries are used to find and prove that black holes exist. not part of this course, of course, but the Star and Planet Formation course, sorry, the Planets in Search for Life course will discuss this as well next semester. If you want to sign up for that one, then the same formula that we just used is also the one that discovered planets around other stars. So of course, planets are also another ultimate unseen companion. They're far too faint to see directly, and therefore you only prove, well, certainly the first ones to be discovered were proved to exist because of the fact that they, it's still a binary system. It's just the planet is much lower mass than the star, but it still does the same thing. So it's effectively still a single line spectroscopic binary. And so the same formula was used to discover planets around other stars. So despite it being the most complicated formula in this module, it is probably the most useful in terms of finding amazing discoveries. Okay, so that's that. I'll leave you with another little task. Okay, just go back to those rate of velocity curves to get yourself familiar with what's going on there. So I'm just going to show you another one in a moment. So I'm asking you to, work out what it is you have to measure from those graphs in order to get the amplitudes of the rate of velocities of the two stars. And to get you thinking about that a little bit more carefully, what's the rate of velocity of the center of mass of the binary system from that type of data as well. So don't forget that the whole system might be moving towards us or away from us. In fact, it's bound to be. Okay. And so you need to think about that a little bit. So probably think about this first, and that will then allow you to do that part. Okay. So here's a rate of velocity curve, as before, rate of velocity against time. So what's the rate of velocity of the center of mass, and what are the amplitudes of the two stars? How do you measure them off this graph? Okay, so that will leave you for this one. So I'm going to put an email announcement around as well, but just to let you know that there won't be any lectures in week 6. So week 6 next week, I won't put out any recorded lectures, and that's because all the physics students on the module are having midterm assessments in all their other modules, not in this module. So there won't be any recorded lectures in week 6. Okay, just to give them a break from the lectures to revise and carry out their assessments on their other modules. Okay, but the live workshop in week 6 will go ahead. Okay, so that's still in week 6 on the Tuesday. Okay, and also a heads up, of course, that in week 7 we will have the second of the multiple choice questions as well, assessments. Okay, so I'll leave that there for now. And when we come back, we've basically finished stars in the module, and so we will then start on galaxies.